Good day for everyone. Thank you so much for this presentation. We are the group number 8 and we're talking about the chlorination process in the water purification plant. We stayed in the last step of the demand methodology, implement and control. In the company background, we have the product is drinking water. The most important activity is the chlorination process. The location is in Guayaquil. The supply chain is this, and the most important customer is the water consumers. Here with that, we have the thing you can see in this slide. The problem focus in this case is since April 2019, the Guayaquil water purification plant has increased to 6% in the average range of product out of specification when the company standard is the 2%. The objective focus basically is decreased 2% from 6% to 4% in the period of 4 months. Our G definition in this case is the percent of product out of a specification in the chlorination process, and we use this equation. Continuing with the implementation plan, we have the most important ideas. The first one is the standardization, and we do this with the KANBAN system to reduce the extra inventory and reduce the product out of a specification and do this. The second one is do the verification system between the machine and the operation workplace with the app. In the above, you can see the schedule for the implementation.
This is our future model. Okay, to transport, waiting line, boiler machine, mixing machine. Regarding the simulation of the models, in the case KANBAN is implement, the car leaves the mixing machine to the boiler machine with the aim of the having as the leading inventory as possible in the waiting line. In this case, having more than 5 in the inventory, the bottle stops in the activities until it reaches 2. In the other hand, for the next solution, the verification process, new actions were simply assigned to the mixer part so that it can perform better. For the number of the replication, in this case, we first work with the minion are having a replica value of the 17, while in the power test, we got a value of the 15. Therefore, the value 17 was taken as being higher. In the same way, the verification process, there are not many chains, therefore there will also be 17 and 50, so 17 being the largest. Show output variable. Consider the average that is obtained from 61 pallets of 200 liter tanks. It can be seen how the percentage of defects decrease for both solutions. This one, they had a chance at all, but the other inferencing variable will be detailed with the one to choose. For BONFERRONI methods, the value of the two solutions we consider of union with respect to the current model gave us a result that the tree has strong evidence. So other actions will have to be seen that can be determined with the solution of choose. Show other output variables. More replicates we made to see how the variable behave. This is another type of the variable that significantly influence the width in the waiting line simulation. In this case, in the KANBAN, it generates an inventory of the 70 pallets, while in the process verification model, it generates the same as the current model of the 17.8 inventory. So, therefore, the KANBAN implementation could be a potential solution. Cost-benefit analysis is needed.
Then we have the process analysis, stability analysis with a conclusion. Both cases reach a p-value rating down 0.05. Therefore, the models are capable. In the same way, for capacity analysis, conclusion with the value CPK and the level sigma, we conclude the model are capable. Report line metrics, the social reduction of workload and the quality department by 30.23% and the financial reduction cost in inventory by 89.61% and environmental reduction of residual chlorine waste by 30.23%. In the economic benefits, we can see the reward cost reduced, cost of residual over time. We conclude reward cost reduced, cost of purchasing extra, overtime costs.
We have a visual control A3. So we have chlorination process in a water purification plant. In context, we have a standardized criteria for the change in kilogram of chlorine is deficient. Actual situation, we have on-label bulbs and pipes, and outdated instructions. In objectives and goals, we have made a collection of chlorination activities and generate standardized operational procedures. In protection action, we have what of the instruction, who, plant manager, how verify that the instructions are correct, and we have label pipes and bulbs, who, plant manager, and how check that the equipment is properly labeled. We have the control indicator, monthly residual chlorine percentage. Now we have the control and reaction plans. And we have what compliance with the review of the chlorine dosing system. Why the personnel can control the quantity to be dosed according to what is showing on the screen. Where in water purification plant, in chlorination process, how verify that there are no different values of those of chlorine using. And who supervisor. And frequency, monthly, and reaction when the dose of chlorine entered and dose existing in the tank are different. And the second, that is verify the chlorination activities and operating procedures are correct and complete. Why decrease the required waste costs among others, where in a chlorination process, and how create an online capacitation program for operators, who operations coordinator every 3 months, and when operators have not been trained or process not followed. And finally, the percentage of product out of specification average in residual chlorine decreased from 6% to 4% during shift 3. The operators were trained and reward costs and cost of purchasing extra raw material in residual chlorine and overtime costs in production and quality department were reduced. In recommendation, we have established a periodic verification plan of the chlorine dosing system and established the capacitation as part of training for new operators. Thank you.